I'd like to tell you a few of the things that we have been working on, where we try to put together artificial intelligence and scientific computing, and I will try to relate this on how we can explain phenomena related to fluid mechanics, and also how we can understand perhaps some of these algorithms that we are using in order to predict and to optimize and to model phenomena in fluid mechanics. I have tried to adapt a little bit the talk, not only to be about fluid mechanics, even though there's a lot of fluid mechanics, to a little bit also to have some applications on the molecular or atomistic level, because I see that many of you are working on this. So let's take it from here, and I would welcome anytime you would like to interrupt this presentation. So first of all, the people who have done all this work, I'd like to acknowledge in particular Guido Novati, Pantelis Vlachas, and Pascal Weber, Daniel Vachli, Won-Min Bieon, and Mihail Hadjimanolakis, as well as many of the other people whose names that you see here on this slide. So since we are at UCLA, I thought that since we're talking about explanation implies a why. So there is this wonderful book, the Book of Why, that explains some of the seminal work that has been done by Judea Pearl. So Judea Pearl presents these ideas, and he says that humanity is on the ladder of causation. So he considers the first part in the ladder association, and that's the place where you're seeing, you're observing, you create relationships between phenomena. And he's using an example from, let's say, a medical case. You sneeze, I sneeze, did I catch a cold? So as if you read this book, at least that's what I understood, where machine learning is today is basically on the level of association. Now, on the other hand, if you want to go up the ladder of causation, you want to understand something, then that's the time that you're intervening. That's what actually babies do often. They break things, they move things, and when they see what happens to them in response to their actions, maybe they're learning from it. So the second example is, what if I take an aspirin, what will happen? So as you will see in my talk, I believe that one of the scenarios that takes us from the association to the intervention is a particular form of learning that is called reinforcement learning. So I will be talking a little bit about that, and I will try to discuss how we can explain what is it that reinforcement learning does, and how does it help us explain physics. And finally, the good news or bad news is that according to Judea, there is a part that where automation and machine learning will never touch, and this is imagination, retrospection, understanding, and these are human traits, and I think one has to be respectful whether to understand what if the aspirin is the aspirin that stopped my headache, or maybe it's something else that I did. So I subscribe very much to this ladder of causation, and as I said, I'll show you some steps in part 2, some attempts in part 2. The conference is talked Explainable AI, but with my poor English, I always try to understand what's the definition of explanation, what is the difference between interpretation and explanation. So I look up some dictionaries, and here is one, which at least helps me to understand things. So interpretability is when you're looking at a model, let's say a neural network weights and features, and then you try to determine a given output by interpreting the model's weights and features. So you kind of like interpret how what is the particular weights that the neural network has. Now, explainability is a little bit more human-centric, where you take the model and you try to explain the machine learning behavior in human terms. And then what you try to do is you have to discover a meaning between input data, attributions, and model outputs. So there is this is a difference, at least I distinguish, and now I want to focus on this part that we say I want to find the meaning between input attributes and model outputs. So the other thing is, okay, we discussed explainability, but now what is artificial intelligence? I guess it may mean a lot of different things to a lot of different people. So I like this part that Bellman said, that it's the automation of activities that we associate with human thinking, activities such as decision-making, problem-solving, and learning. So it's this, the keyword is an automation. And there is another slide about intelligence that comes from one of the pioneers of artificial intelligence, John McCarthy, where he says intelligence is the computational part of the ability to achieve goals in the world. And there is also something that I observed that here it's actually not necessarily talking about what's inside the system, but what is the goals that the system is trying to achieve. So what, according to the definitions from McCarthy, you don't necessarily have to understand what are the mechanisms of a particular system, but what you're interested on the outcomes of a particular system. So that's actually when artificial intelligence is most usefully understood. So sometimes maybe there is a contradiction here, because when we try to say explainability, maybe we imply mechanisms, and actually mechanisms in terms of human terms. So I'm not so sure that in the end these two things can come together, but it's an exciting area of research. There is also criticism about this need for AI. Should the AI models be explainable? I mean, there's a lot of things that we do that work. We do them all the time. Even numerical methods. Take molecular dynamics, if you like. What's the explanation for molecular dynamics in human terms? Yes, the first term is something that depends on the hydrogens, atoms coming together, but how about the second one? It's a heuristic. It's the power of the 6 to the 2, so it gives you 12. So AI models do not necessarily need to be interpretable to be useful, and actually, for many of the drugs that are prescribed on a routine basis, people don't really know how most of them really work. On the other hand, to continue the controversy, here's something that came out a few days ago. There is the reproducibility issues that haunt healthcare AI. So it seems that AI and healthcare are important things, but we still need to be able to have reproducibility. And I think one way to have reproducibility is to have explainability, because maybe you can take out what are the things that work or not. So I think we're trying to do explainable AI. It's not, in my opinion, settled that such a thing is consistent with the two terms. But nevertheless, it's a very interesting effort to try to put these two things together. So how we have been doing things, how we have been explaining things. So here is an example where I will try to explain a physical system by doing uncertainty quantification to the system. So here is a language of explanation that goes through Bayesian uncertainty quantification. So you're all familiar with molecular dynamics simulation. Here is a carbon nanotube. These are buckyballs in water. You're looking into a potential, and finding what is the gradient of this potential gives you a force field. Now, you have a lot of different force fields. So here's the Lennard-Jones potential I was talking about. Here is water-carbon interactions that you do. So you can decide that you have some parts that are, you have the modeling parts. So why do you have this number 12 over there? You have parameters that you have to worry about. You have also computational issues, your thermostat, your time step, and so on. And finally, if you look at the data, these are data of the contact angle of water on graphite. You have a lot of uncertainties in this data. So what is uncertainty? So what do people do? Classically, that's what I actually have been doing when I was doing molecular dynamics. You look at experiments. So you can look at a contact angle of water, of a droplet of water, and then you look at the binding energy Z, the carbon-oxygen, and then you pick a parameter and you write a paper. Someone else picks another parameter and writes another paper. Many people write a lot of different papers by using different parameters. So what do we learn from that, or what have we learned from that? Let's look at another way. So usually what you do actually back here, I don't have this slide, is you find an experimental value about what should be the contact angle, and then you should go back down and find out what should be the binding energy. But is that enough? Now, we have been looking at uncertainty quantification for Lennard-Jones potential. So let's look at take only one potential. So let's take the Lennard-Jones potential, and let's look at two parameters of the Lennard-Jones potential. One is the depth of the well, the epsilon, and the other one is the cutoff length that you have. Because you have terms that are 1 over r to the 6 and 1 over r to the 12th, you can understand that at some point you are computing a lot of zeros. So what is the classical thing in molecular dynamics is that the bigger you make this R cut, the better off you are. Now, how do you do uncertainty quantification? Well, you're using this machinery of Bayesian uncertainty quantification, where you have the model, this m of theta here, and then you have an error term that here it has a zero mean. The mean is the model. It has a covariance. And then you're using experiments where you get some data and you try to find what's the probability distribution of your parameters with respect to the data. So you do this Bayesian inference. You have to compute some high-dimensional integrals and so forth. Let's assume we understand and we know how to do all these things. And now we look at the results. So here's the results that we got when we use some experimental results for contact angles of water. What you see here is you see the cutoff and the epsilon, and you see the places where you have the highest likelihood. And now you start to have a dialogue with your model because you can interpret these probability distributions in different ways. First of all, you can do marginalization with respect to the epsilon, and then you get a probability distribution for the R cut. And then there is another thing that you do, which you can marginalize with respect to R cut, and that's what you get from the epsilon. And for me, the interesting thing that you can observe in this diagram and this diagram, it's actually that you have maximum likelihood for the smaller R cut. I would have expected this to be very large for very large R cut, but what you find out is you find out that the smaller the R cut you have, the better it is. So an explanation that you can draw out of this, and I'll be happy to argue with you, is that basically your model is wrong, and the less you use it, the better off you are. That's the explanation of what this thing tells you, and as I said, I'll be happy to discuss that. So that's one way of arguing about models using uncertainty quantification and interpreting the probabilities that you get there. We will see a lot more things like that later. Now, we move to machine learning. So I'd like to show you a couple of algorithms that we have been developing where we actually try to combine machine learning and scientific computing, and I will try to discuss interpretability, explainability of these algorithms. So we try to combine numerical methods that are usually exact. When you're solving a partial differential equation, you are interested of doing something very well, deterministic, etc. And at the same time, you try to combine this with machine learning. And machine learning is a statistical learning technique. It has statistics. So when you try to combine the two together, and one should ask, why do you want to combine the two? I'll tell you a few reasons in a moment. You're trying to somehow make a marriage between two things that are not necessarily very compatible. But nevertheless, I thought that you can think in terms of alloys, that you can think of something that is for the numerics to be a pure metal. And one of the issues of the numerics is that sometimes the numerics that you do in order to be exact, they become very expensive. So maybe you want to introduce some modeling components and you want to replace some parts of the exact numerics with machine learning. Maybe you want to use the exact part and also couple it with a few things from machine learning in between. And there's, of course, all sorts of combinations of the two. So this schematic diagram is to try to explain to you a couple of the machine learning algorithms that I'll show you next, and I'll show you what we learn and where we go with these things. So I'm going to be combining numerical simulations with recurrent neural nets and autoencoders, and I'm also going to be combining models and numerics with reinforcement learning. So this is what I call computing alloys. Now, let's look at the first one. There is a technique that we published recently. It's called learning the effective dynamics of complex systems. So what is a complex system? A complex system, classical complex system, Kuramoto-Shivashinsky equation described by this PDE that I have up there. It's a nonlinear PDE, but I have a parameter that actually helps me to decide what's the chaoticity. The larger the parameter, the more chaotic the system. I can solve this system right in a numerical method, but now I don't want to, I claim that this is very expensive, and can I stop solving the equation after a certain time by solving the PDE with this method? and can I use machine learning in order to do predictions of this complex system? So how do we do that? Well, what you do is you take some data from the simulation, from some early times. You add a model with the recurrent neural nets with a LSTM. You train it, you optimize it. And then after you train it, then you try to do to predict the dynamics of unseen data. In our case, we are looking at the dynamics. The reference dynamics are given here. We know them. But we're not going to use all of them. We're going to use a part of them down here. This is the full space dynamics. We go through a process where we're actually learning not on the full dimension of the system, but we do a compression, and we are learning in a reduced order space. The reduced order space, reduced order dimensions can be through SVD, or it can be through autoencoders, as you will see in a second. So what is it that I do is I run some simulations, I collect some data, and then I want to know if the neural net that I have just trained is able to produce the system dynamics further down the road. So I'm using recurrent neural nets, long short-term memory. I'm not going to go into that. And now let's look at the results. Again, I'm training on the reduced order space, and I can always project because here I have SVD back to the full space. I'll show you what else I can do later. And so right after the training, the predicted and the exact, they are looking very well. Now I keep going further in time. They're still doing well. I'm still doing well. And after a while, I start to fail. And this is a chaotic system. And actually, I'm going to fail very, very much. So machine learning fails to predict the dynamics of complex systems. And actually, the highest the complexity of the system, the more the machine learning algorithms fail to do so.
So even if you change to perturb the parameter, because it's a chaotic system, even if you perturb the parameters of the model a little bit,
the sensitivity depends on the chaoticity of the system. Yes.
So, and you are not sure on the parameter, right? It's a model.
The parameters, I have learned them. I have learned them from the data that I have.
But you have an uncertainty of the parameters. So
I can have uncertainty on the parameters, yes.
So how is the machine learning model worse than a model with different parameters?
It's, what do you mean worse, or what?
I mean, you said that you diverge.
Yeah.
You diverge also if you change the parameters a little bit.
Yeah.
So it's just another model.
Yes.
Yeah.
There's nothing magic about neural nets. That's what I'm saying.
Yeah, exactly.
Yeah, I agree.
But I think perhaps another way of putting it is does it matter that it diverges? So
I'll show you. I'll come back.
Okay.
Let me be critical, and then we'll try to fix it.
What I tell when I teach these things in my class is that the trajectory per se doesn't have any meaning. It's the statistics.
Very good. We'll come to that.
Okay.
Because actually, the statistics, there is something you can do.
Yeah. Sorry for the spoiler.
What?
Sorry for the spoiler.
No, I love it. That's actually why I came here. So thank you very much. Please continue. So now you can do this. You can have the system, and you can actually, it's interesting. If you have less chaoticity, you observe that you more or less stay in the same manifold. I'm going to start already using this term. And when you increase the chaoticity, you are completely off. Okay? So now, are there ways to fix that? Well, we have been looking at different methods. There is actually a method where we are, in addition to doing the neural network, we are learning the statistics of the system. And then by learning, what is this? Yes. So this is the system that before was completely chaotic, and we lost it. But now we complement with a Wiener process that actually preserves the noise of the training that we had. So by adding noise to the simulations that we have, we find that we are able to stabilize and to more or less keep the system not from diverging. But nevertheless, if you're looking at the exact trajectory, you find out that it's not there. The interesting thing is when we publish these papers where we show actually that the thing that does not predict chaotic systems, one of my students says this Quanta magazine has an article where we are referenced that we predict chaotic system. But I said we do not. And he says, well, they say we do. So you go figure out who is right. But as we say in all these papers, we do not. And we compare a whole bunch of different methods, and we argue when to use what, and so on and so forth. So maybe the correct way is yet. Maybe it does not yet, but and maybe it will. So now we were not satisfied with this, and I wanted to still make this thing work. So there is an algorithm that many of you know. It comes from my friend Yannis Kevrekidis. There is also other algorithms like by Wainani and Humano Wadi and others. The late Jared Marsden, he did the flavor. Wainan did the HMM. So let me talk about the equation-free framework. And the idea of Yannis was that you have a system and you can propagate the micro scale of the system, but then you can also find a way to go to the latent space, much as I was doing. And then what Yannis was doing back then, he was using integrators like Runge-Kutta and things like that to advance the latent space dynamics. And then the Achilles heel, no pun intended, for Greeks is that at some point you had to go back to the full dynamics, but then how do you go from less information to more information? You can do SVD, but SVD was limited, and yes, there was a lot of papers that came out from this effort, but in my opinion, they always had some limitations. So after looking at this idea for 20 years, I thought there is a very interesting way that you can actually go back out from fine scale from latent space to full space dynamics, and the way actually that comes out is by using autoencoders. You can go with an encoder to a latent space, use a decoder to go back out into the full space. So in a sense, you are training through your data a compression and a decompression operator. You can actually have stochastic decompression operators, because this way you can have different samples. And for the integrators, we think that these recurrent neural nets with long short-term memory, especially when you are in the latent space where you don't have enough data, actually they're even better than transformers than people are using today. If you have few data. If you have a lot of data, transformers win. So we took these three ideas and we said we're going to use this to propagate the macro-scale dynamics, and we're going to do this for restricting and averaging, and we're going to do this for lifting. As everybody does, we gave it a name. We call it learning the effective dynamics, and this is what we do. We run a little bit the micro dynamics. Then after that, we have latent space time steps, and then we do the RNN, as I did before. And of course now, as I showed you before, at some point I'm going to fail. Now, we have different ways of detecting when we fail. I can give you just a very brief way, because we are playing with them. When you go down to the latent space, you can decide, since it is inexpensive, you can have many initializations or perturbations of your latent space. So you can run many RNNs. And when you see the variance of the simulations increasing, then that's an indication about the time that you need to go back out to the full expensive simulations. How do you go back out to the full expensive simulations? With the decoders that you have trained so far. So you go back out, you get again on the right manifold, and then the hope is that you're able to go back and forth between the two. Now let's look at it the Kuramoto-Sivacinski. So we have, again, the evolution Kuramoto-Sivacinski. The interesting thing that we found is that for the Kuramoto-Sivacinski, there's a paper that says that effective dynamics lie on an 8-dimensional manifold. Indeed, the autoencoders, they seem to find this cutoff at the 8 dimensions. The SVD that you see here, it did not detect this. So we like these autoencoders as a way of going to latent space dynamics. And now here's the results. Here's the results, actually. I think in this slide, I think we never went back to we didn't do the back and forth. We just stayed in the latent space all along. So now you look at the latent space, and people who are looking at explainability, at least myself, I understand nothing. That's what's going on here, and I don't know how to interpret this. But then if I take this and I use the decoders, this is the behavior of my system. And now you look at what the LED produces and what's the original, and you can see that they look alike, but they are different if you look at, depends how you look at them. If you look at them time step by time step, they're different. Now maybe if you look at them statistically, our eyes maybe cannot do statistically, but we can do a phase space, and you find that the phase space that the LED is capturing, the phase space that the reference space is capturing, are actually quite similar. The speed up that we get is hundreds, is the order of hundreds, and 2 orders of magnitude. I don't like that the error doesn't go down very much when even I go and I do the alternations. But again, there's a lot of open points that we have into that. Now, you can take this, and as a prelude of the more fluids that you will see later, we do study now a flow, which is flow past a cylinder. For you that you understand what is flow past a cylinder, actually, maybe I need to jump to somewhere else. I'll talk a lot about vortices, so let me introduce you to vortices. So this is, if in the morning when you take your spoon and you move it, the rotation that you see here, these are what this rotation of the fluid is called a vortex. Vortices is what the airplanes produce. That's why you see this tower sending up smoke, and then you will see the smoke starting to roll up. So it's basically showing you the rotation of the fluids. You see it in pictures like that. This is over islands, and you will see a lot this flow past a circular cylinder. The blue means that the fluid rotates this way. The yellow rotates this way. There is a uniform flow all along, but because we take the curl of the flow, the gradient of the flow, you see 0 where the flow is uniform, and you only see the vorticity. So the vorticity is a compact way to explain fluid mechanics. It took me 30 years to come to terms with it. I hope you have, in these 30 seconds, an idea of what these blue and red things are going to be. Fluid rotating like that or like this. If you know the vorticity, you know everything, by the way. So it's an interesting for incompressible fluids. Let me go back to, after teaching you fluid mechanics, let's go back to the LED. Now, I asked the LED to predict a flow simulation. And now what I ask, actually, I have, usually we do these grids. We have a grid, we have 3 velocity components, 2 velocity components and a pressure. And the grids we use is 512 by 1024. So you are close to 500,000, more than 1 million points, actually. And now this is the reference simulation. This is the prediction that we get. And now the compression is that we're using only 2 terms in the latent space to predict. So now this thing is actually seems to be doing really well. And not only the root mean square error is quite bounded, but also derivative quantities like the drag is very well captured. And you see that you have only 4% error. Well, you basically are 2 orders of magnitude faster from something that is already very, very cheap, and you make no mistakes. Now, the bad news is the problems that we had, when actually a lot of people, I need to tell you this, a lot of papers in machine learning and fluid mechanics, they show you a Reynolds number of 100, and then they tell you the problem of fluid mechanics is done. It's not done, because the Reynolds number decides how fine the scales of the flow are, how chaotic the system is. So whenever someone says, I have done the flow of 100, everybody can get the flow of 100, including us. Ask them, what about the Reynolds number of 1,000? So you ask me, what about the Reynolds number of 1,000 for LED? And here's the answer. And the answer is that it's not so good. And it's not so good, and I'll try to explain to you why it's not so good. So this is the reference, this is the prediction, but okay, if I look at the drag coefficient, I have an error of 20%. I still get my speed up, but my root mean square error doesn't really go away. I don't understand why all these things are the way they are, but I found something that I found interesting. And what we found interesting is that the biggest errors, they happen around the surface of the cylinder. Around the surface of the cylinder for bluff body flows, that's where everything happens. The vortices, if you have a flow that's going by, the only place that the flow tumbles and vorticity gets generated is on the surface of the cylinder. So when we do the autoencoders and we use equal weights for all the parts of the autoencoders, we're not putting physics into our machine learning method. So what we are looking into now, and I have results that are positive, but I cannot show them at the moment. We have results where actually when you pay more weights, more attention to weights in the vicinity of the cylinder where you know the physics are, then these results, they become better. But again, this is that you need to do some kind of input from physics as to where you are measuring. There is also about how you propagate things in the latent space dynamics. There's a lot of different things like Cindy and reservoir computers. We found that the LSTMs, they were consistently having the lowest error. But there is one more thing I want to say about cylinders, and actually it's going to be this slide. And the numbers that you see here is the amount of money that I bet that machine learning will not be able to capture these flows, at least for the time that I'm alive. And this is the flow behind a cylinder. And what you see is this is a state-of-the-art simulations at these Reynolds numbers, where we resolve every detail of the flow. We have not imposed symmetry. If the flow has the minuscule error, it would become an asymmetric shedding. And you get some very, very fine structures. This has been done with adaptive mesh refinement. It's one of the best simulations in terms of accuracy and care that I have ever been involved. And I think it will take a while for machine learning to catch this. Yes?
So first, this is incredibly beautiful. I want a background, I want a poster.
Yeah.
and two, I mean, I guess that if the cylinder has a minuscule imperfection,
yeah,
this will make
the flow becomes. We have done also the cases where we can. Usually, what you do if you wanna, so the flow becomes unstable. Usually, what people do is they run it, and then your numerical errors are gonna get you, and the flow becomes unstable after Reynolds number of 100. Or sometimes you do this to the cylinder, and then so we do that. It looks as beautiful, but I thought that this is more spectacular because you can see a lot of beautiful things between the different things. You see how the flow separates. These vortices go away, but they're going to come down and slam onto the flow. Here you get the Kelvin-Helmholtz instabilities that are coming back and slamming. So there is a lot of scaling and a lot of beautiful things you can do. But I sincerely do not think machine learning will get there. And I'm on video now.
Can you put some of the necessary physics into the machine to like the symmetry?
Yeah. What do you mean when I do the simulation?
No, when you do the machine learning.
Yes, you can. The best things that I have, at least for doing machine learning myself, is this LED at the moment. There is this thing called physics-informed neural nets, etc., that I will show you that they are really bad. It's another presentation where I can show you actually at least maybe for high-dimensional problems and for problems with a lot of parameters, they may make sense, the physics-informed neural nets. I don't want to get into that. But for this stuff, no, they don't work. Now, come to molecules. So you have more questions. Now, how about the LED on molecules? So I don't do any of the sophisticated molecules you all guys do. I took this very poor man's protein, the alanine dipeptide, and I was very much interested how the LED is going to do in the dynamics of this system. So this is the phase diagram of the Phi and the Psi. The hydrogens are missing there. So here's the results. The results is that you take now certain parameters. We take about 24 parameters to describe the dynamics. And then the LED is basically 1 degree of freedom. Is basically a free energy equivalent that it's operating on. And then what we do is that we find that it reproduces coarsely the statistics. So what the
system is intrinsically two-dimensional.
It's intrinsically because of the Phi and the Psi, yeah.
You can reduce it to 1?
Yeah, well, you'll see, can means the following. Look at the diagram that I get.
Missing,
I have holes here. And I don't get these holes.
You do it in 2?
I don't know. Maybe we could try.
Yeah, because in 2, I'm pretty sure you can do it, because it's intrinsically.
I'm happy to interact with people. I worry if I will be able to do it in 2 if I have not done the training in the right area. If I have done training, yes, that's the thing. And the thing that I will show you is actually depending. So let me show you quickly what you get. This is the free energy prediction of the latent space. The thing that I like is that the minima, they correspond to different minima in the landscape. But you see that there are certain minima in these areas that I was not able to stochastically interpolate. But what I have done is I have a method that does stochastic interpolation. I think there is a lot of interesting things that have been done. And to play a little bit, we tried to see what happens if you come over here and you take out data, you don't give it data there. Does it discover that? That it discovers. It's able to figure it out. So we take out data from here that it discovers. And now when it's actually interesting, we remove this one, it discovers it, and actually it's able to populate things. So it tries to do something in the stochastic space. It's a start, and I'll be happy to, anybody who wants to play with LED and different proteins and interact, I'll be happy to do that.
Things like this, I think it's very important to put some constraints, like some of the region where it goes, it shouldn't go because there are atoms overlapping. So if you put some physics constraint, maybe you can even learn something.
Yeah, maybe, yeah. But I don't know enough molecular dynamics or protein dynamics to do all that, and I just wanted to put it as a proof of concept and all this explainability. There is a whole bunch of papers here. I want to move to the better part of my talk now, in my opinion, which is about reinforcement learning. We see a lot of learning about neural nets. There is also this multi-agent reinforcement learning, I call it. For those of you who have not seen reinforcement learning, this is something that a lot of behavioral psychologists and zoologists did. There is this famous experiment by Burrus Skinner, you know Pavlov's dog, but there is also Burrus Skinner and the pigeons.
The two pigeons are at either end of a small ping pong table. One pigeon...
This was at Harvard in the 50s.
The pigeon pecks the ball back across the table. If it goes past one pigeon...
He's going to score, and the door is going to open here, and he's going to eat. And then by playing the game, now he's going to eat, and this guy has closed the door. So by playing that game, they learned to play ping pong by doing that. Now, the application of this, I don't know if you have seen it. It's a wonderful article if you have nothing to do. They were trying to do bombs, and the idea is that you put the pigeon inside the bomb, and then you train the pigeon to look at a certain area, and then when the bomb is flying over this particular area, the pigeon pecks on a button, and then the bomb falls in this particular area. It's called Pigeon Pilots. You can read this article. And this is Burrus Skinner. How many of you have heard of Verbos? Verbos is one of the pioneers of putting the first theory with Bellman of reinforcement learning. He was also at Harvard in applied math and or collaborating. So that's a little bit the history. Now, today, reinforcement learning is everywhere. You see it in games, the game of Go. You do it in all these androids that they teach to do different things. What is reinforcement learning? Reinforcement learning is that you have a system, and I'll come over there again. So you have a system, an environment. You can observe it somehow. And then you have a state of the environment, and then you have a machine in here, a neural net here, a recurrent neural net, that tells you what action you get to interfere with the system. In this case, the actions are coming out by sampling the Gaussian probability distribution. Gaussian probability distribution has a mean and a covariance, and this mean and the covariance is being trained based on the states of the system. You have some weights in here, and we call this mapping between the states and the actions the policy. So the policy gives you a mean and a covariance of a Gaussian probability distribution. Now you make an action, the environment responds, you get a reward, you get food, and you try to maximize the long-term reward summed under the actions and the policy that you're acting. And you do that, you come back here, you change the weights, and then you play the game. This is stochastic optimization. Now, this is a game that you play many, many games. And now one of the key questions in reinforcement learning is, since you're playing many, many games, you don't necessarily, since you have all these experiences, all these tuples where you have experiences of what happened, maybe for every new case that you're presented, you don't have to go and do everything again because this is expensive. So this is what the people in reinforcement learning, they call experience replay. And there is a lot of issues with experience replay, which actually I was surprised that they had not been addressed. Actually, you will realize in a second what is experience replay. So as I said, you take you maximize an expectation under a probability distribution, but you don't like this probability distribution because it's expensive to form it, etc. but you have other probability distributions from which you sample, and these are your experiences. So when you bring an experience, then what can happen is this ratio can become 0 or infinity. And also, being physicists, you know this important sampling. If you sample from another probability distribution than the one you should be sampling from, the two probability distributions should be alike. We found that this issue had not been extensively addressed, and that's why you get a lot of instabilities in reinforcement learning. And then what we did is we corrected this behavior by introducing a trust region for this ratio. We reject samples if this is large, and then we have a penalization based on a KL divergence between the online policy and the offline policy. Now, when we published this paper, call it Remember and Forget, Experience, Replay, and we applied it into the classical problems. So now you can, so this guy is our guy. This is the guy of these people here who are quite prominent in reinforcement learning, and now you can explain the behavior that our guy is better because the android kicks itself and flies, while this one is doing steps. I'm joking, but it is better. And to our surprise, actually, we find that we outperform many state-of-the-art. I don't want to say everything in terms of the reward that you get over time. And we have an explanation of why we outperform, because for our case, we are on purpose minimizing the Kullback-Leibler divergence as time proceeds, but they don't pay any particular attention to that. They have something about the threshold, many of them, but you see here the Kullback-Leibler divergence between the online and the experiences that they bring is quite large. Another thing which is interesting, you don't see a lot of reinforcement learning in physics, and when we try to do something, actually we try to put this guy to stay behind a cylinder that is setting, we found that a lot of off-the-shelf algorithms don't work for complex dynamical systems that you find in physics. So when we did this refer, it was something that we were aware of this. So where do you find these things? So here's the one thing that we did, is there are some fish that they like to be behind obstacles, and they seem, trouts in particular, they stay behind rocks, and they manage to stay there, so there is a flow. The fish stays there, and what people have done experimentally is that actually the fish, they're able to slalom, and actually there's particular areas where the fish like to exist. So that's a particular situation. So what we did is we did a reinforcement learning for that, that now I have an agent. My agent is a swimmer. It has certain states, relative position, angle, velocities. I also measure shear stresses on the surface of the body. And now this guy can increase or decrease the amplitude and its tail beating frequency. This is the actions that it takes. And then the reward is minimize the swimmer's energy output. So what we found, which was very interesting, we found that, we found that we indeed can keep the swimmer here. Now there is a flow coming in, so this guy stays stationary. But what we found is that if this guy were to swim with this velocity, it would use about 45% more power than if it is behind a cylinder. So being in a dirty wake somehow, it saves you to save energy. It actually makes sense because this guy produces energy into the flow. If you know how to capture it, then you are able to extract energy from the flow that is there. So now this is some of the results, Reynolds number of 1,000. So now what we were very much interested in, in anticipation of this workshop, we wanted to understand what is really happening. What does this guy do when it manages to swim in this place? So we can actually we have what is difficult now to understand is that when you have this reinforcement learning, I guess same for neural nets. The neural net basically does a mapping between 16 states and 5 states because this is the mean and the covariance. And this is the value of this is a diagonal covariance. That's why it's two means. for the actions, and then we also dump out the value function. So this mapping 16 to 5 was not something we could visualize. So then what we decided to do is we want to see if we do a marginalization in all the states that are participating in this function, and then we try to find out how the states and how the actions are behaving at particular spaces x and y in the domain. So, so this is what the policy looks like when you do this marginalization. When you look at the policy over space, you see that they have this positive and the negative thing that it does to the curvature. I guess the positive is when it tries to do this, negative is when it tries to do this. And the interesting thing is we find a value function that actually also finds a distance away from the cylinder. And it's actually interesting that fish, where they agglomerate when they harness energy from cylinders, they also have a certain distance. The comparison is kind of like, okay, wishy-washy, but it's kind of encouraging. This is, again, the value function, the value of your actions. So now we want to understand this, and a new thing, that a new toy that we have in order to explain. I was introduced by Kranmer about this program that he has, this PySR, which seems to be a very nice piece of software where he does fast and parallelized symbolic regression in Python and in Julia. And the idea is that you want to describe what is the behavior of your system. So what you do is you put down a few operations like minus, division, multiplication, plus. You put down some kind of expressions that you would like to have. And then you get out an expression like that, which tells you what your neural net is doing. And hopefully this is much easier to interpret than actually the full system. So I actually bet with my student that nothing is going to come out of that. So I lost, because it's actually interesting that you look at the policy, and this is the curvature that came out. And then we put this data into this PySR. We give it a whole different options that it can do. And actually, it found a very interesting expression. It found this parabola, yx, as to what should be the behavior of the curvature. So that's now a much more easier to communicate result as to what should be the behavior of the curvature for a fish that is behind a cylinder. Now, of course, to see if this explanation is valid, we take now, and we don't do reinforcement learning, but we give to these guys the simplify control rule. So to my surprise, actually, it was able to maintain course for quite some time, except until it failed. But even like that, instead of doing reinforcement learning, now you have an open control rule, which is a parabola to tell your fish how to swim. And now we found actually that if you add one more degree of freedom, this is the frequency of the tail. Before we just gave it only the amplitude, but now we give it also the frequency of the tail. The policy gives you, when you do the respective marginalization, gives you something like that. This symbolic PySR gives you something like that, which is not, I told him not to put 6 digits, but anyway. So it gives you something like this, but which is not so easy to explain, but nevertheless, it gives you a very nice looking behavior about the rules. So now you apply this rule, and that's where I lost the beer, because this thing, when you combine both, is able to maintain course for quite some time, and at some point, it's going to get close to the cylinder, and going to get much stronger vortices than what he expected before, and that's going to throw it off from this. Maybe we need to have rules for different parts of the domain. So it's my contribution to explainability by saying you take the policy in reinforcement learning, you map it with symbolic regression, and you hope to extract very interesting rules. I'm running out of time. There's a lot of different things we do with reinforcement learning. I'd like to show you no more a lot of fish. So actually, another thing we do is, let me show you this actually, why not? So we do, well, I'll show you two things. We're interested in this. we're doing some very large, where is the other thing now? Hold on. And then we are able to do, the reason I'm interested in these simple rules, so this is 300 fish. This is one of the historic simulations of 300 objects swimming freely in Navier-Stokes equation, producing all these vortices. But now we want them to be controlled, and we want to have simple rules for them. That's why the symbolic regression is quite appealing. Before we do the 300, we do the two of them. And what we found interesting is that actually we can run different objectives. And just to tell you the thought process with reinforcement learning, okay, I pick out some states and actions. And here I ask the fish that is behind, we ask it to swim on this line. So after many tests, it was able to swim on this line. It has as a state where is the other fish and learns to swim on this line. The interesting thing was that the power of deformation for this fish dropped. It's using the one behind is more efficient swimmer than the one in front. And then we actually, I'm not going to go into that, using different neural nets, we found actually deep recurrent neural networks much better than feed-forward networks for the case of reinforcement learning. This guy goes in and out. And the other thing we found is that we said, now let's maximize for efficiency. And then we were able to maximize. This guy goes behind, is able to extract energy, and you get a very high gain. Now, 2D is one thing. In fluid mechanics, if you want to do 3D, whatever cost you have here, you multiply by 1,000. If you're lucky, because now you have a third dimension. That's the grid you have to use in 3 dimensions. So we cannot afford that. And we said, what have I learned from 2D that I can use in 3D? So as a human being, I thought, what have I learned? I've learned that if you swim behind another fish, your efficiency is better. Now, when we go to 3D, this is the vortices. And now from the fluid mechanics that I have taught you, do you think that this fish is efficient? The answer is no. It's as efficient as this guy because it almost swims in a clean wake. Because this guy here produces vortices like that, and in 3D, the vortices go sideways. Okay, they're not right behind the body. So now, if you look at 2D and 3D, this is a 2D flow, and this is a cross-section of a 3D flow. So what you want now, we could not afford to do reinforcement learning in 3D, but what we want to do is to learn to teach this guy, to make this guy stay in areas like that, so he can harness the vortices from there. We use the PID controller. There is a little bit more hairy details. I'm not going to tell you all that. I'll show you the results. I have to go through the, there is a lot of analysis that we did, but again, reinforcement learning was a very useful tool. But now we can do simulations like this. This guy harnesses vortices, is 20% more efficient. And of course, you see there is this row of vortices that is wasted. And then, of course, you can do this, where you have, this is a very interesting configuration. You get a total of 30%. And even in this mesh, where you have 2 fish in front and 1 behind, this guy is able to capture all the vortices. Last thing to leave you about reinforcement learning is that you can do one more thing with reinforcement learning. And the one more thing you can do, which I think is quite interesting and fun and simple, is to solve equations. So how do you solve equations with reinforcement learning? You have an equation you want to solve, and then you decompose the solution vector into something that you can resolve and something you cannot resolve. For fluid mechanics, this is a mean field quantity. For people who do coarse-grained molecular dynamics, this is coarse-grained molecular dynamics. So then, instead, what you have to resolve is you're solving this equation. And of course, you don't know this, but how every plane and every car is designed by coming up with models. Maybe here, this is your coarse-grained molecular dynamics model. So can you tell what's the next line? What I'm going to do next? That's right, by reinforcement learning. which is that's proposing to use the mean field quantities to learn the collection using reinforcement learning for a dynamical system, except that there is a problem. And what is the problem? The problem is that at least when you go to fluid mechanics, this is your grid. And usually in 3D, you have 32 cube. 32 cube gives you about, what is 32 cube? It gives you almost about 500,000 states. So you cannot train a reinforcement learning algorithm with 500,000 states. But then the next idea that I thought, most of all the results are from others, this one is mine. It's so simple. It's that you can now consider the grids not only to be discretization elements for the equations, but they can be also agents that learn. So now you have multi-agent reinforcement learning. And now the grid points can be both, can be discretization points for the equation and learning machines. And now you break down the complexity because you are learning locally. So a lot of details are going to be bypassed. I'll show you a result on something called homogeneous turbulence flow. It's one of the classics in turbulence simulations where you have a closure term, and then what we do is we're using some local and global states, and then we're learning the Smagorinsky coefficient, and we're using as reward, the reward actually is interesting because you can have DNS or experiments. You can formulate or shape the reward as you like. This is the reward. This is the difference between the energy spectrum on the coarse-grained versus the fine-grained results. And state-of-the-art has been, I'd like to say, the green and the purple, which is the dynamic and the standard Smagorinsky model. This is increasing the chaoticity of the flow. We have done training on these Reynolds numbers, and we are able to extrapolate to much larger Reynolds numbers. In one case, we are learning in only one Reynolds number here, and then we try to see how we can downscale or upscale for different Reynolds numbers. But the best policy we came up, this blue one, seems to be doing really well. We have done this also in other types of flows, again, incorporating physics. A lot of physics in reinforcement learning goes into what states you have. If you just put the velocity field in the states, it's not going to work. You have to have some kind of invariance of the flow. In this particular case, we're doing homogeneous isotropic turbulence. We used as invariants the local ones are the eigenvalues of the gradient tensor, the stress tensor, because these are characterizing an isotropic homogeneous flow, and we have some global quantities. There is a big art that we try to take the part of the art out as to what are the states in reinforcement learning, what are the actions, but I think it's exciting lines of work. I'm going to stop and thank you, and I'll be happy to take any other questions.